Last time we were talking about stoichiometry, and we talked about a couple of different sort of types of stoichiometry. We talked about just sort of basic stoichiometry problems. And basic stoichiometry problems, you're really only given one piece of information, either a reactant, a product, something of that nature. And you need to figure out, how much product you produced or maybe how much reactants you started with. And in a basic stoichiometry problem, really there's sort of four steps that you want to follow. The first one is you always want to start with a balanced equation. Again, nothing in terms of stoichiometry works correctly if you don't have a balanced equation. You then want to take whatever they give you and convert it to moles. Um, so a lot of times, if you're given grams, obviously we would use the molar mass there from the periodic table to allow us to convert to moles. And we want to do that because really from the balance equation, that's really where the stoichiometry comes from. It's those coefficients. And those coefficients in the balance equation basically represent the moles of everybody that's there. So we could come up with sort of a mole to mole relationship and use it really as a conversion factor. And usually that's because in a stoichiometry problem, we are given a piece of information about something we're not really interested in, and we want to find out something else in the equation. So we use that as, again, a sort of a conversion factor to go from one thing to the next. And then the fourth step is to take those moles that you usually or end up with at that step and convert it into some other type of unit. Again, it may be grams on the back end where you might have to use molar mass or, and again, any other type of conversion. We also talked about last time as well, sort of limiting reagent problems. Limiting reagent problems occur because usually in a reaction, there's usually one reactant that pretty much gets used up first. And the one that gets used up first is what's known as the limiting reagent or limiting reactant. And the one that you have there in sort of plentiful supply is what's referred to as the excess reagent. And it's important in the terms of limiting and excess because it is really the limiting reagent, which is the one that determines how much product that you can make. So if you just think about a reaction as we go from reactants to products, usually to make the products, you need sort of both reactants involved, maybe. And obviously, if you run out of one of them, you're not going to be able to make any more product. So when you do have a limiting reagent problem, there's a few different ways we kind of talked about doing it. Um, you basically need to at some point sort of figure out which one is the limiting reagent. And a good way to kind of do it is sort of like I showed you. You could kind of do it in through an ice table, as we talked about. We basically convert everybody into moles. We do initial moles. We represent the change with an X. And also, when you do the change part, you want to take the coefficients into account as well, because that really does the mole to mole relationship for you. And basically, what we do is at the end there, we set each of the reactants equal to zero. And whichever one produces the smaller amount of moles will be your limiting reagent, and your other guy will be your excess. And the nice thing about sort of the table approach, as we saw last time, is you can very quickly sort of answer every question that might be asked to you in a sort of limiting reagent problem. You could very quickly, if there's maybe multiple products, figure out how much of the other products you would produce. If there's also, for example, how much of the excess reagents left over, you could do that relatively quickly as well. So it's sort of a nice beneficial way of doing it. It allows you to get to all these sort of questions very quickly. But again, as we talked about last time, if you remember how to do limiting reagent problems in another fashion, you definitely could still do that. And again, the two sort of popular ways of doing it, other than sort of an ice table, is basically just do two separate stoichiometry calculations, one from each reagent, and basically see which one produces the smaller amount of product. And that would be your theoretical yield and also your limiting reagent. So that's a very common way, just two separate calculations, one from each reactant to the product of interest, and whichever one produces the smallest amount is the limiting reagent. Another common approach is to basically do a small little calculation between, say, the two reactants and figure out, do you have enough to use up all of one reactant with the other? And you compare that to your starting amounts and see if you do have enough or not. In addition, how we know it is a limiting reagent problem is very simply, in a limiting reagent problem, you're given enough information in terms of the reactants basically to get the moles. So if you have enough information given to you to calculate the moles of all the reactants, then it definitely is a limiting reagent problem. If you don't have enough information basically to calculate the moles of everybody on the reactant side, then it's sort of a basic stoichiometry problem. I think we also finished up talking last time as well about percent yield. And percent yield is basically the actual yield divided by the theoretical yield times 100. The actual yield, as we talked about, is essentially what it sounds like. It is actually how much you produced when you did the reaction or the experiment. And that number is usually given to you in the problem. The theoretical yield is the one that you need to actually calculate yourself most of the time. And again, that's based on the equation. That's your maximum amount of yield that you can produce. And you would calculate it based on the equation, maybe a regular stoichiometry problem, maybe a limiting reagent problem. Any questions on any of that stuff that we sort of talked about last time? Okay. So I think this is where we left off, if I'm not mistaken, on this example here. Just come back. All right, so why don't you take a few minutes here and work it out. We want to determine the percent yield in this reaction and give you some information in case you don't have a periodic table handy. Carbon is 12.01, nitrogen 1401, oxygen 16, I think that's everybody, hydrogen 1.008. All right, so take a few minutes to see what you come up with. Again, we're starting with 100 grams basically of each, and we produced 120 grams. What is the percent yield here? Okay, so let's take a look and kind of see how we're doing. So again, first off, we are given 100 grams of ammonia and 100 grams of carbon dioxide. So we basically have the grams of both of our reactants. And obviously, if we have the grams of both our reactants, we could get to the moles of both of our reactants, which automatically should tell us this is a limiting reagent type problem. We're looking for the percent yield, which is basically the actual divided by the theoretical times 100%. And that is what this number is right here. This 120 grams is the actual. So we do need to find the theoretical here. So we do need to do basically a limiting reagent problem here. So really the first couple of steps are sort of the same. We want to make sure that it's balanced. So I do see some coefficients. So I'm going to assume here that it is balanced. We then want to take whatever they gave us basically and convert them into moles. So we have 100 grams of ammonia, ammonia being NH3. So we will go to the periodic table and help convert that. So 100 grams of NH3. If you go to the periodic table there and add up 1401 plus 3 times 1.008, that gives you something like 1703 grams per mole as our molar mass from the periodic table there of NH3. And that gives us something like 5.872 moles of NH3 here to start with. We also want to do basically the same thing here with our other reactant, which is our CO2. And we will take 100 grams of that. We'll go to the periodic table, one carbon at 1201 and two oxygens at 16 each gets us something like 4401 for the molar mass. Again, we're going to put it on the bottom so the grams cancel. Grams cancel and grams cancel. And that gets us something like a starting moles for our CO2 of 2.72. I missed the 2 there. 2 points. Try that again. 2.272 moles of CO2. First off, any questions up to that point? So we're just converting basically the moles, always pretty much what you want to do here in a stoichiometry type problem. All right, so again, I'm going to show it to you using the ice table. If you, again, are doing it a different way, in the end, we all should hit the pretty much the same answer when it's all said and done. So if we did our ice table here, we just want to kind of start with the equation. And initially, it's going to be those moles that we just calculated. So for the NH3, I believe, again, it was 5.872. For our CO2, 2.272. And again, here we could assume that we are not starting with anything on the product side at this case. Now, the change part is really the important part. Again, we represent it with an X, but we also need to take into account our coefficients, because really this is the part that does that mole to mole relationship, really the stoichiometry part of it. And since we're assuming that this reaction is heading to the product side, our reactant side should be decreasing. So we represent that with a minus 2x, again, the 2 for the coefficient, a minus x here for our CO2, again, the coefficient is 1. Now on our product side, we're assuming that we're gaining products. So we're going to go with a plus x, again, coefficient there is 1, and a plus x on the end there for our water. Bringing everybody down, and again, I'm just going to kind of get rid of the moles part here so I don't have so much words in my numbers. So we're just going to kind of carry everything down. First off, any questions on the ice table, what it looks like, why we got any of those numbers? Okay. So once you sort of have this table set up, what we're going to do now is basically figure out which one is the limiting reagent. And we're going to do that by basically setting each of these guys equal to 0 on our reactant side. So we would have 5.872 minus 2x equals 0. We're going to bring the 2x to the other side and divide by 2. So basically divide by 2. And we will end up getting an x value of 2.936. We'll do the same thing over here. This will be 2.272 minus x equals 0. That's a pretty simple one to solve there. X is going to equal 2.272 moles. So what we're looking for here is the one that is the smallest number of moles. And in this case, it is our CO2. So what that means is our NH3 is our excess reagent. This guy here would be our limiting reagent. So the CO2 in this reaction is the limiting reagent. The NH3 is the excess reagent. And again, we always use the limiting reagent here to figure out how much product and everything else that is going on. Now, the nice thing again about this sort of table method is we can very quickly, get to our answer here. So it is all these x's pretty much in this table is the x value that we just solved for. So in this particular case, we're interested in the NH2 So we know that the moles of NH2CO there is equal to x, which means we have 2.272 moles of it. And if we want to convert it into grams, we would go to the periodic table and get the molar mass of this guy. So we got 2 times 1401 plus 4 times 1.008 for our hydrogen. We got 1201 there for our carbon and a 16 there for our oxygen, giving us something like 6006 grams per mole. Again, the moles are going to cancel, and that gives us 2.272 times that, about 136.5 grams of our product here was produced. This again is going to be our theoretical yield because it is the one that is based off of the equation. Any questions on that there? That is going to allow us to basically figure out the percent yield. So our percent yield would be our actual, which was given to us at 120 grams, divided by our theoretical, which is 136.5 grams, times it by 100%. And it looks like for this guy here, we're shooting at something like 87.91%. Not too bad. Remember, percent yield, we're looking for high percent yield, not small. First off, any questions on any part of that calculation there? Now, since we're looking at this, again, sort of the benefits of this sort of table is, for example, if we wanted to know how much water we produce, we could very simply just go to the table and we see that the moles of water also equals x, which means we have 2.272 moles of water. We could go to the periodic table, get the molar mass of water, which is 18.02 grams per mole. And very quickly, we could determine that if I want to know how much water I produce as well, we produce something like 40.94 grams of water. And again, we can find that very quickly. Also a common sort of question is how much excess reagents left over. So we can also very quickly kind of go back to our table and figure out how much excess reagents left over. The excess left over, it's a very bad excess left over, would be 5.872 moles minus 2 times x, which would be 2.272. And if we did that, 5.872 minus 2 times 2.272 means that we have about 1.328 moles of our NH3 that's left over. And obviously we could use the molar mass there like we did at the beginning to figure out how many grams that would be. And that's about 22.6 grams. We'll go 22.6 grams of NH3 is left over from our 100 that we started with. So you can see it didn't take a tremendous amount of work to kind of go back and sort of solve for everything that you could possibly ever want to know in a problem like this. And again, that's sort of a benefit of this method of solving these problems. It sort of puts everything right in front of you very quickly to get to those end answers. Any questions on limiting reagents, excess reagents, stoichiometry, how to do those things? Okay. So what I'll do is I'll scroll through here, and I think I have sort of alternative methods. So I'll just scroll through in case you want to, watch it again later on, as it puts you to sleep or something. If you're watching the video again, you can kind of see another method here to get to the end. Stuff. So, and again, you can see we obviously get the same answer using the other method as well. Okay. All right. Any questions on stoichiometry at all? So we're going to then kind of move on to solution a little bit here, and we're going to tie back into stoichiometry as well. So let's talk about solutions, and we're going to talk about some different concentrations that involve solutions. First off, a solution is a homogeneous mixture, and homogeneous mixture again means that pretty much everything mixes. Everything looks the same throughout. And there's really two parts to a solution. There is the solute, which is the smaller part of the solution. So that is the smaller part. And there is the solvent, which is the larger part of the solution. So typically when we take something and we dissolve it in something like water, we're making a solution. And a reminder that there is a difference when we talk about, again, those two sort of symbols, L, which is a liquid, and AQ. L, which is a liquid, is basically just a pure substance by itself. So, for example, like water, if we just had H2O by itself, that would be a liquid. If we took some solid sodium chloride, for example, and mixed it with some water, that solid sodium chloride would dissolve, and it would dissolve into the water, and we would get an NaCl solution, a sodium chloride solution, and that would get the aqueous symbol. So again, if you see something with the L symbol, basically means that, it's just one sort of substance by itself, nothing else mixed in there. If you see something typically with the AQ symbol, that usually means, for the most part, that it's two things kind of together, and usually we have that smaller guy and that larger guy to mix together. Now, oftentimes we think about solutions as always being sort of in the liquid state, if you will, like a soft drink, for example. Water would be the solvent, sugar, CO2, all the bubbles that you see would be the solute. A little hard to see, but it is actually air is this guy here. At least it's hard to see on my side. I don't know how it is on your side, but that says air, I think. And actually the major component of air is nitrogen gas, not oxygen. It also has oxygen, argon, CH4 as well. And those would be solutes as well. Solder, sort of a solid state. That's obviously a gas. Lead and tin basically together. Although most of the time we kind of think of solutions more in that sort of liquid state, but technically speaking, you could kind of have a solution that is in some other states as well. So when we talk about concentration and we talk about solutions, there is a most common sort of unit of concentration, and that is molarity. And molarity is big M, and basically it is moles per liter. Really, it is what it says here, moles of solute per liter of solution. Most people just talk about it in terms of moles per liter. We could kind of think of this almost as a formula. We can use this to solve for any of those three things. So for example, if I want to solve for liters, that is moles divided by molarity. If I want to solve for moles, which is a very common thing that is done, that is liters times molarity. And again, here, this is very, very common sort of calculation that is done a lot. This is a very common way when we're dealing with solutions, how we can kind of get to moles rather than using something like molar mass. Um, now, when they say something like, hey, you have a 4.5 big M sodium chloride, that is known as a 4.5 molar sodium chloride solution. What that big M really means is you have 4.5 moles of sodium chloride per liter, or you can really use it almost like a conversion factor. A liter has 4.50 moles. I highly recommend as we go through these problems, we sort of use molarity to really convert it into those two units and not leave it as big M as you're doing calculations. A lot of times when people kind of leave it as big M, they forget all about the liters part. You know, they have no idea where it is or it's still there or not. And they just think, oh, big M moles and all that. And they forget all about this. So it's really a good idea to sort of convert it into sort of both units so you can at least kind of see them. Number always stays with the molds. It's always 1 liter sort of for the bottom as well. Now, when we use molarity and we do want moles here, we do need to convert things into liters so that all the units do cancel out correctly. You can technically multiply milliliters times molarity, but what you actually get is not moles on that point. You get what are known as millimoles. And that's because sometimes molarity is thought of as millimoles per milliliter. And that's because the two millis cancel out and you're back to moles per liter, ends up being kind of the same number and stuff like that. So just keep in mind, if you do multiply this molarity by milliliters, you're actually not getting straight moles. You're really getting millimoles, which might get you the wrong answer. So always a good idea. Always convert it to liters when you have to deal with molarity and multiplying it. That way, everything will be in the right unit. All right, so we have an example here. What mass of potassium iodide is required to make 500 milliliters of a 2.8 molar potassium iodide solution? So why don't you take a minute or two to see what you come up with? Potassium is 3910, it looks like. And iodine is 126.9, it looks like. All right, so see what you come up with here. Okay, so let's take a look. So we're looking for what mass, which is grams. Potassium iodide is required to make 500 milliliters of a 2.8 molar solution. So obviously we're dealing with molarity. So if you're not sure maybe where to start, you can kind of almost check off what is given to you. So we do have the molarity given to us. Although we don't have liters, we do have milliliters given to us. So that's almost just as good. So again, here it would make sense probably to solve for moles. And that would make sense because we could go then from moles to grams using the molar mass. So we need to do a couple of things here. First off, our 500 milliliters needs to be converted to liters. So you can move the decimal place, divide by 1,000 if you like, which will do it for you. Gives us 0.5 liters. Now, if you want, you can again use the molarity as almost like a conversion factor. So that basically means that we have 2.8 moles of Ki over a liter. Or again, you could use it in the opposite sort of direction, like a conversion factor. So if I kind of take the conversion factor approach here, we would start with our 0.5 liters. We would use it on the left there. It gives us 2.8 moles per liter of Ki. Our liters are going to cancel each other out. And that's going to get us 0.5 times 2.8, like 1.4 moles of Ki. But again, here we do want grams, so we're going to need the molar mass here of Ki. So we're just going to add basically both of those numbers together, 126.9 from the periodic table plus a 3910. Looks like 166. So 1.4 moles of Ki and 166 grams per mole, moles on the bottom so that they cancel. And we end up with about 232 grams of Ki in this particular case. Any questions on that calculation there? So what does this number really mean? This number really means is if you picked up the bottle of Ki, you scooped out there about 232 grams of it, threw in some water to get a final volume of 500 milliliters, gave it a shaky, mixy, all that good stuff there. You will end up with a solution that has a molarity of 2.8 molar, provided you didn't spill it when you did the shaky or mixy part of it. Any questions on that calculation there? Okay, let's try another one here and see. Let's say, what is the molarity of a solution that's made by dissolving, and we'll go with 42.5 grams of calcium chloride and enough water to make 250 milliliters of solution. Calcium is 4008 on the periodic table, and chlorine is 3545 on the periodic table. All right, see what you come up with here. Okay, so here we are looking for the molarity, which means we basically need moles and liters. And in terms of that, we again don't have directly liters, but we pretty much have the next best thing here, which is milliliters. So we pretty much got that. We don't have moles. We do have grams, so that's nothing. We can basically convert it into moles. So that's probably what we want to do first. So we're going to take our 42.5 grams of calcium chloride. Again, going to the periodic table there, adding those up, a couple of chlorines at 3545 and a calcium at 4008 gives us a molar mass of, we'll call it 111. And we're going to divide by that. And that gets us 42.5 divided by 111. And we'll call it 0.3829 moles of calcium chloride. So we now have the top part. We do need to convert our 250 milliliters into liters. Again, you could just move the decimal place 3 places to the left or divide by 1,000. It's going to give us 0.25 liters. So we got pretty much everything that we need to put into our answer here. So molarity would be 0.3829 moles divided by 0.25 liters. And that was going to get us about 1.53. Now, in terms of the units, they don't cancel out. So again, it would be moles per liter. So again, the number would stay with the moles part and it's 1 liter. Or you can just write 1.53 big M is another way, obviously, that you can sort of give the answer there. Any questions on that there? So obviously molarity is a really important unit of concentration, probably the most commonly used unit of concentration for solutions. We use it a lot, and we're going to use it a lot in terms of calculations coming up, liters, molarity to get to moles and stuff like that. While we're talking about sort of concentration and molarity, let's talk about what happens when perhaps we're maybe not interested in the whole thing, but maybe we're just interested in, say, a particular ion or what the ion's concentration is. So, for example, if we had something like 0.25 molar sodium sulfate, and if we want to know what the concentration was of the sodium ion in there and what the concentration of the sulfate ion would be in there, we can basically do it very much like stoichiometry. So when we take something like sodium sulfate, it is going to break apart into 2 sodium ions and a sulfate ion. And how concentration is affected is if the whole thing here is 0.25 molar, it is basically a 1 to 2 relationship in terms of the sodium ion. So what it does to the concentration is we actually take the sodium ion and we would have to multiply the concentration by 2, kind of twice as concentrated, which means if we were interested in just the sodium ion, the concentration of the sodium ion would be 0.5 molar. When we look at the sodium sulfate and the entire guy over here with our sulfate, it is a 1-to-1 relationship. And that means it's basically 1 times our original concentration. And we end up with the same concentration here for our sulfate. So you can see here when we look at sort of ions and concentrations, they are obviously not additive. Those two don't add to each other, but they are proportion. So you may say, how come we double it and stuff like that? What I just did is really the way you could do it. Basically, whatever the coefficient is times the original concentration by it when you break it apart into ions. The long version of this calculation is this. If we went 0.250 moles per liter of our sodium sulfate, we know that for every 1 mole of the whole thing, we get basically two sodium ions, right? There's basically two sodiums there. And that's how the moles of the whole thing cancel. And I should put the mole down. We are left with obviously what we just ended up with, zero point 0.5 moles of sodium per liter. So that's sort of the long version of it. The short version of it is whatever that coefficient is, you multiply the concentration by, and that will give you the concentration of the sodium ions in that particular guy. Question on that. So why don't we try one? Let's say, what is the molarity of, and we'll do phosphate ion in a 0.75 molar sodium phosphate solution here. Actually, let's do both and the sodium. Okay, so if we look at this again, what you want to probably start with, since we're going to be looking at the ions here, is we want to see basically how this breaks apart. And this would break apart into 3 sodium ions and a phosphate ion here. And again, you could kind of do the long version of the calculation if you like, or the shorter version. So it's basically a 1-to-3 relationship here in terms of the sodium ion. So we would take the whole concentration there and multiply it by 3. And that gets us obviously 2.25 molar would be our sodium concentration here. It is a 1-to-1 relationship between that and the phosphate. And that again would be 0.75 molar for our phosphate. And again, it's basically sort of its ratio, if you will, or concentration. You basically get 3-to-1 in terms of sodium ions for every phosphate ion you toss in there. So it's basically 3 times as concentrated in terms of the sodium ion as it is in terms of the phosphate. And the reason it all works out that way is because for every phosphate you need 3 of those sodiums to come together. So that's how it comes back to basically the 0.75. Question on how to calculate molarity, grams, liters, ions, concentrations, any of that stuff. So this is a nice way of making a solution, by the way. That's a volumetric flask, if you could kind of see it. My screen is kind of gone, but volumetric means expensive usually. Usually volumetric also means there's usually only one marking. And that one marking represents the volume of it. So whatever this may be, we'll say this is a 100 milliliter volumetric flask. Basically, you start with your solid. You would put a little bit of water or something in there, your solvent. Usually you wouldn't fill it right to the mark at the beginning. You would keep it kind of below the neck here. That gives you a lot of room where you could kind of start mixing this really good and starting to get it to dissolve. And once you got it pretty much dissolved, then you can take it pretty much and fill it. And you usually want to go very slow at this point. I guess it's good we're not going to be doing the titration experiment in person, because this is usually what happens. People fill it in and just go, oh, I guess that line was just a recommendation, right? We could just go way above it, right? It's okay. I'm sure it's not that important. And then they mix it up really good and they go, oh, shoot, I could just pour it out, right? The answer is no, you cannot pour it out because you already dissolved your solute. So when you would pour out that extra little bit of liquid, out would go some of your solid that you put in there, and you would screw up the concentration. So then this is sadly when we go, that is the waste container over there, go dump it out and start again. But usually when we use something that's volumetric, again, usually very expensive, and usually just for reference sake, usually that is a 2 decimal point. So if that was 100, we would usually say 100.00 milliliters. So usually we go to about 2 decimal places. When you use something that's volumetric, again, usually it has just that one line. So the next thing we're going to talk about, though, is with solutions is oftentimes we do get solutions in a more sort of concentrated form. And a lot of times what we need to do with those solutions is to do the process known as dilution. And obviously when we dilute something, it's not as strong, if you will, if you want to think about it that way. It's like when you get your drink right before you come to class, right, with all your ice in it. And then after class or several hours, you go back to your car, all the ice is melted. You still drink it because you're like thirsty and say, how bad could it be? Then you drink it and go, probably shouldn't have done that maybe. But all the ice melted, right? And we created more water and we diluted it down. It obviously doesn't taste as strong as it did when you left. And that's basically the process of dilution. In the process of dilution, the moles of solute, which is really important in solutions and sometimes overlooked, is this idea. When we make a solution, we'll talk about those circles, I guess. Those circles represents basically the solute, or really the stuff that's dissolved in the solution. And it's really that solute that is the only thing there to react. So when we do a dilution, we're really just adding more solvent to it. So why does that affect the molarity? It affects the molarity because molarity really is moles of solute divided by liters of solution. So what happens when you do a dilution is you're not really touching the top part here. This stays the same. You're basically adding more water, which is essentially going to be increasing the bottom part here. And that's going to make the bottom number larger, and thus your molarity will go down in that case, because you're basically adding more water, increasing the volume of solution, and the molarity will drop down. So most of the time we are only adding something like water. Just so you know, water doesn't always have to be a solvent. You can, something else can be a solvent, but water is a very common solvent for a lot of ionic compounds, a lot of polar compounds. So it works really well for a lot of things. In a later chapter, we'll talk about things where it doesn't work so well. But a lot of times all we're doing is, again, just adding some more water here. And we do have a dilution equation, and usually that dilution equation is this one, which is M1 V1 equals M2 V2. And this is usually like before the dilution over here on the left-hand side. This is after the dilution over here on the right-hand side. It doesn't necessarily have to be that way, but that's usually sort of the arrangement there. M1 V1 equals M2 V2. M1 and M2 are obviously molarity. M1 is usually the more concentrated or stock solution. M2 is usually the more dilute solution. V1 is the volume of concentrated solution you would need, and V2 is usually your final volume. Now, some people will also use this dilution equation as C1 V1 equals C2 V2. You'll sometimes see it written. And C is really just a generic term for concentration. So although most people will use the M1 because molarity is the most common unit of concentration, you technically don't have to use molarity here. It could be other units of concentration, some of which we'll talk about here in a later bit in this chapter. Things like perhaps percent mass to mass, percent volume to volume, percent mass to volume. So these are all different concentrations that technically you could kind of put in here. But again, most people will probably stick with this guy because that's usually the most common unit of concentration. Now, this equation here actually is one where you don't have to necessarily convert the volume into liters. If you want to, you can. If you want to leave it in milliliters, it's okay, as long as both volumes here are in milliliters. And that is because if you took the first guy and you times it by milliliters, you will get millimoles. And if your second volume here is also in milliliters, when you would divide it, those millis will cancel out and you'll be back to moles per liter. So in this dilution equation, if you don't want to, you don't have to convert the volume into liters. When you're using molarity, you can times it by milliliters. You just got to make sure you divide by milliliters on the back end. Or if you want to be safe, you could just convert it into liters and it'll work out the exact same way. Any questions on that there? All right, why don't you take a shot at this here and see what you got? We want to know, how would we prepare 60 milliliters of a 0.2 molar nitric acid solution from a stock solution that has a concentration of 4 molar? So take a couple minutes, see what you'd come up with. Okay, so this is a dilution problem. So everybody sort of understand what we're looking at. We basically have a container sitting there that is 4 molar nitric acid. We want to make another container that has a total volume of 60 milliliters and also has a concentration of 0.2 molar. So we can use our dilution equation there. We could do our M1 V1 equals M2 V2. In this case, we can go M1, which is our 4 molar, usually the more concentrated guy. V1 we don't have. We want to keep our two other numbers together. So this is going to be 0.2 molar and our 60 milliliters. Again, here, we don't have to necessarily convert it to liters. You can if you want to. That's going to give us 0.2 times 60, and then we're going to divide it by 4, and that's going to give us a V1 of 3 milliliters. So since I did not convert it to liters, my answer ended up being in milliliters here on the back end. Obviously, if you converted it to liters, you would end up with liters as your answer when you did it. first off, any questions on that calculation? So what does this mean? That is really 3 milliliters of the nitric acid, which means we would go into our 4 molar bottle and we would throw it in here. And we would put our 3 milliliters in here. We want a total volume of 60 milliliters. So the question is, should I throw 60 milliliters of water in there? And the answer should be no, you should not do that. Because if you did that, that would be 60 milliliters of water plus 3 milliliters of what you already put in there. That gives you a grand total of 63 milliliters, which is too much volume. So a lot of times they ask sort of how much water should you add or you need to add. So to figure out how much water you need to add, that usually is V2 minus V1. So in this particular case, our V2 was 60 milliliters minus our 3 milliliters that we put in there. That tells us that to our 3 milliliters of nitric acid that we dumped in there, we need to put in there 57 milliliters of water. Don't ask me why the water's red. I'm not sure. It's Halloween. All right. So we got 57 milliliters of water with our 3 milliliters of our nitric acid. That gives us, again, a grand total of 60 total milliliters. Again, given in a good mixy, shaky, shaky. And you will then have a nice solution here that is 0.2 molar in terms of its concentration. So a very common mistake sometimes people make when they go to do a solution or make a solution is just that they go, oh, the total volume is like 100. Let me put 100 milliliters of water plus whatever else I tossed in there. And again, that's going to give you the wrong total volume and thus obviously the wrong molarity. Question on how to make that there. So why don't we try yeah.
Sorry. When you do the shaky, mixy.
Yeah. You put a lid on it as well before you do that.
Right. Probably with acid would be a good idea.
I guess.
Yeah. Will it separate, or is density not an issue with?
It won't separate here. Again, something, for example, like nitric acid and water, they're soluble in each other. So when you would mix them, they would mix together. And that's what I was talking about a little bit earlier, that although we oftentimes think about when we dilute something that we always like toss water in there, water is not necessarily always a good thing. So for example, if we weren't doing, say, nitric acid here, but you were doing something like hexane, which I think maybe we saw in that earlier lab this semester. And if you took the hexane and decided I want to dilute it with some water, those two guys don't mix. And that's because hexane, as we'll talk about later, is basically non-polar and water is polar. So in terms of what this guy's trying to do, the water is trying to use hydrogen bonding. The hexane is trying to use dispersion forces, and they really don't mix. And in that case, they really won't mix and make a solution because you'll see those two different layers. So remember that a solution really is a homogeneous mixture, which means technically everything should mix. So if you're going to make a solution, you would want to obviously choose a solvent that will actually mix with it. So when you look at it, it all should just be one solution. Or if you're going to make it from a solid and a liquid, you would want something like water with an ionic eye that would allow it to dissolve. Other questions on that there? Okay. So let's try one here. Yeah, why not? We'll try it on this slide. Why not? This is a nice slide. We'll do it on this one. Let's say, if we want to know how much water do you need to add to 125 milliliters of a 6 molar sodium chloride solution to make we'll go with 1.25 molar sodium chloride solution. All right, so figure that out real quick.
It was 3 milliliters, and then the water was 57 milliliters.
Okay, so let's take a look at this here. Again, we're basically starting with sodium chloride. We're ending with sodium chloride. The only difference here is the molarity is going down. So again, no real reaction happening here. This is just an indication of some type of dilution. So our M1V1 equals M2V2 would be a good move. Here we could go with our M1, which is 6 molar. Our V1 that kind of goes with that is 125 milliliters. Our M2 would be our more diluted solution at 1.25 molar, and V2 we don't have. So if we solve for V2 in this particular case, we end up with, looks like 600 milliliters. And that would not be the answer, though. That is basically the final volume of the solution that we would make. So this would be the final volume of the solution that we would make. So in this case, again, very common dilution questions. They oftentimes ask about the water. So basically what that means is, again, to find the volume of water, we would need to do that. We're going to take our final volume, which is 600 milliliters, minus our initial, which is 125. And that's going to tell us that we basically need to add about 475 milliliters of water. So again, here, if we just took the whole entire thing, which sometimes happens, the 125 milliliters, and we dump in there 475 more milliliters of water, and again, mix it up, we then should have a solution that has a molarity of 1.25, and we would actually be at a total volume at that point of 600 milliliters. Any questions on dilutions?
How do we get a molar solution in the first place? So how would we get 6 molar NaCl solution?
You would have to dissolve the proper amount of solid in the case of sodium chloride to get you there, and the proper amount of water, depending on what volume, I guess 125 milliliters. So you would do this calculation here. You would just use the molarity type calculation. So we would, if we wanted, it was 125 milliliters, right? 125 milliliters, which is 0.125 liters. We would times it by the molarity of it, which was 6 molar, right? Moles per liter. That would tell us that 0.125 times 6 is 0.75 moles of sodium chloride. And then we can multiply that by the molar mass of sodium chloride, which is like 2299 plus 3545. And we would need to put in there about 43.83 grams of sodium chloride in that 125 milliliters, basically, of like water. And you should technically have a 6 molar solution at that point. Yeah.
Thank you.
You're welcome. Other questions? Which it's a good amount to scoop out, I imagine, to kind of get you there. Yeah. All right. Other questions on dilutions and those type of things? All right, so I'm going to actually clear this so we can actually see what's written on here. Let's see here. All right, so we're going to talk about sort of using molarity and volume, and a lot of times we'll use molarity and volume in stoichiometry problems, and a lot of times we'll do stoichiometry problems, and they're basically done the exact same way as the stoichiometry problems that we talked about earlier on in this chapter. They may be a basic stoichiometry problem, they may be a limiting reagent stoichiometry problem, but really the main difference when we deal with something that involves solutions is how we get moles. And normally, like we've been doing in the previous examples in this chapter, we would take the grams, we would use the molar mass, and we would convert it into moles. But when we're dealing with solutions, a lot of times we don't have information like how many grams was in there or something like that. We oftentimes have the molarity given to us and the volume. And we can use the molarity and the volume by, like what we talked about before, taking the liters times the molarity to get to moles. So a lot of times we'll do some stoichiometry problems involving solutions. And the one sort of main difference is, instead of maybe using molar mass from the periodic table to do that sort of grams to moles conversion, we could get to moles by taking liters and molarity to get to moles. Also, on the back end of the calculation, when we kind of do stoichiometry problems involving solutions, sometimes we'll actually use molarity sort of on the back end of it. So like the calculations we did before, we had moles and then we kind of converted those moles back to grams. So sometimes when you're dealing with solutions, when you get to the end of the stoichiometry sort of calculation, you'll sometimes use the moles and some volume to calculate molarity, or you may use the moles and the molarity to figure out the volume. So again, sort of on the front end, we oftentimes will use liters and molarity to get to moles. On the back end of some stoichiometry calculations involving solutions, we'll use it to either calculate the molarity of the solution or like the volume of the solution. Now, there's two sort of common ways that we sometimes will use solutions and sort of stoichiometry together. One way is an experiment known as gravimetric analysis. And typically in a gravimetric analysis type of experiment, what we typically do is we mix a couple of solutions together and we make our favorite precipitation reaction occurring. So we oftentimes will make like a precipitation reaction. And when we do a precipitation reaction, we're usually interested in the solid precipitate that's being made. And a lot of times in that process, as you can see here in the first picture, we have a couple of solutions. When we pour those solutions together based on solubility rules, like we talked about, we do get that solid that forms. Again, we're not really interested in sort of the liquid part of it. We're just interested in the solid. So that usually requires some type of filtration. And that's what we see here in the last picture. The last picture is basically vacuum filtration. So instead of like gravity filtration where you pour it in, just wait for it to kind of drop by gravity, kind of hook it up to a vacuum, turn it on, sucks everything through really quickly, and it filters it very quickly. And what we typically would do is, as we were pouring this through, we would collect all of the solid on that filter paper. And if you remember, we were talking about percent yield earlier on in this chapter, and we talked about the idea that sometimes, you know, you can get over 100% yield, and that's usually a bad thing. And this is a very common procedure where that takes place. So a lot of times, as you can see here, when this guy is pouring this in, that solid that's going to end up on the filter paper is pretty much going to soak the filter paper too, with a lot of water and stuff like that. So sometimes people are impatient and they don't wait for this thing to dry completely. And they go, yeah, it looks pretty dry. I'll just throw it back on the scale and see how much I got. And what they end up doing, like we talked about a little bit earlier, was they end up weighing it. And what they are weighing, thinking that that's all my precipitate I made, they're actually getting the precipitate and a lot of extra water weight that shouldn't be there. So it's why it's really important when you do something like this that you actually sort of make sure that it's really dry. A lot of times we'll put it in an oven or something like that, let it sit in a drawer for a couple of days or so to really dry out, so you don't get any of that excess sort of water weight as a result of that. So in a process like this, when you do it correctly, when you do weigh your guy at the end, you will have the mass of your solid, and that obviously would be your actual yield, right? And you can do your theoretical yield based on these two solutions. And again here, if we were going to do our sort of stoichiometry and our theoretical yield, we have no grams or anything here. So again, we probably have molarity and volume. So we would use these guys to get the moles. We could do our stoichiometry calculation just like we did before. Again, the only difference here would be that we're using liters and molarity to get the moles. And we could figure out something like the theoretical yield. And obviously in an experiment like that, that would allow you to calculate usually what you're interested in, which is that percent yield that we talked about as well. So this is a very common sort of process that's done. A lot of times it's usually a precipitation reaction, because in those reactions, obviously you have something that you can isolate like the solid and predict, you know, how much you should get versus how much you actually got. Any questions on that there? Now, more common in terms of solution stoichiometry is titrations. And looking at the clock, I think is probably a good place to actually stop instead of starting this. So we will stop there as well. And it's Thursday, you know, it's been a week, I suppose, right? All right, so we have lab today. We are going to, so since we didn't have class on Tuesday, we're moving